Hello everyone, myself Jitendra Dhakar, fifth year research scholar working in the Chemical Engineering Department of IIT Roorkee. My topic of presentation is pressure-driven flow of ionic liquid through a symmetrically charged contaction expansor microfluidic device. These are the some microfluidic applications by biological and or chemical reagent detection, point of care diagnostics, DNA sequencing, drug delivery, lab on a chip, and microreactors. Here we can see the representation of drug delivery and lab on a chip. The understanding of the microscale flow is significantly important for developing the essential and reliable microfluidic devices for microfluidic applications. And the non-uniform geometries are commonly used for practical applications such as a contraction expansor, T-junctions, or other branching. Now comes on the introduction part. Electrokinetic phenomena is the family of several effects that occur in heterogeneous fluids. The term heterogeneous fluid here means the fluid containing particles or ions. Electrokinetic phenomena commonly classified as electrophoresis, electroosmosis, sedimentation potential, and electroviscous or steaming potential. Our topic of interest is electroviscous effect. So now we discuss about electroviscous effects in liquid flow through microchannel. So the surface of the microfluidic device got charged when it comes in contact with the ionic liquid. Then the charged balls attract counter ions and repel ions, and rearrangement of the ions form a layer that is called electric double layer, and electric double layer is shown here. That is consist of compact layer and diffuse layer. The ions in the compact layer is rigid and the ions in the diffuse layer are free to move. So when the pressure driven flow is applied on the microfluidic device, the excess ions in the EDL moved with the liquid and generates a current that's called steaming current, and the potential related to this current is called steaming potential. The steaming potential drives ions in the EDL opposite to the pressure driven flow and generates a conduction current that drives liquid with them and retarded the primary flow. That effect is commonly called as electroviscous effect. Okay. So here we can see the symmetric representation of the electroviscous flow through 414 contraction expansion slit microchannel. That microchannel consists of three sections: upstream sections, contraction section, and downstream section respectively, where LU, LC, and LD are the lengths of upstream contraction and downstream section respectively. And W is the half width of upstream and downstream section, and WC is the half width of contraction section. And the walls of the microfluidic device assumed to have a uniform surface charge, where ST and SV are the top and bottom wall surface charge densities respectively. These are the assumptions are taken to solve the flow problem. Flow is considered as laminar, steady, incompressible, and fluid flow. And the liquid is considered as incompressible, Newtonian, and it contains symmetric anions and cations and having equal valencies and diffusivities. These are the dimensionless parameters used to solve the flow problem, where RE is Notch number, SC is symmetric number, K is inverse trivial, ST is top ball surface density, SR is surface charge ratio, respectively. Okay, so now comes on the mathematical modeling. So these are the governing equations. Equation 1, where equation 1 is the Poisson equation that relates the total electric potential to the net charge density. Equation 3 is the Navier equation that describes the conservation of each ion species. Equation 5 is the Navier equation, that is the conservation of momentum equation, and equation 7 is the continuity equation. The term F is the extra electrical body force term that is expressed in the equation 6. These are the boundary condition for these governing equations are just shown here. Okay, so with the help of these scaling parameters, the previous equations are non-dimensionalized, and we get the dimensionless equations as equations 8 to 11, and the dimensionless groups are shown here. And equation 12 is the correct continuity equation. At the steady state, it is satisfied at the inlet and outlet of the microfluidic device, and the induced electric field is calculated from that equation. Okay, so these are the computational grid details, and these equations with the appropriate boundary conditions are solved using the finite element method based COMSOL multiphysics software. So after simulating the flow problem, we get the results in terms of total electric potential, excess charge, induced electric field strength, and processor fields. Here we can see the normalized excess charge and double star distribution along the microfluidic device for various surface charge ratio and ST at ST equal to 8 and K equal to 2 and 20. The normalized excess charge led to the excess charge from this equation, where N star is the excess charge. So the clustering of the normalized excess charge occurred in the contraction section as compared to the upstream and downstream sections due to the reduction in the cross-section area. And the absolute value of the minimum excess charge with increases with increasing SR from 0 to 2, because increasing in the SR enhances the electrostatic force near the wall that increases the excess charge. Okay, so absolute value of the minimum excess charge decreases with increasing K from 2 to 20, because K is inversely proportional to the radial thickness. So increasing in the K decreases the radial thickness, that decreases the excess charge. Here we can see the total electric potential U distribution along the microfluidic device for various surface charge ratio SR and ST equal to 8 and K equal to 2 and 20. The potential gradient is maximum in the contraction section as compared to the other sections, because reduction in the cross-section area increases the excess charge and the convective velocity in that section that enhanced the steaming current, and therefore the steaming potential is, therefore the potential gradient is maximum in the contraction section. And the absolute value of the total electric potential increases with increasing SR from 0 to 1 and decreases with increasing further SR from 1 to 2, because increasing in the SR enhances the electrostatic forces near the wall, and that increases the U. But at higher SR and small k, when ideal overlap, the forces are much stronger and resist the charge flow. That reduces the steaming current and further steaming potential. And absolute value of U decreases with increasing K2 to 20, because K is inversely proportional to the radial thickness. So increasing in the K decreases the radial thickness, that decreases the potential drop. Here we can see the pressure P distribution along the microfluidic device for various surface charge ratio and ST equal to 8 and K equal to 2 and 20. The pressure gradient is maximum in the contraction section as compared to the upstream and downstream sections, because reduction in the cross-section area increases the convective velocity in that section. Therefore, the pressure gradient is maximum in the contraction section. Absolute value of the P increases with increasing SR from 0 to 2, because increasing in the SR enhances the electrostatic force near the wall, that increases the wall stress and resists the flow. So the pressure drop increases with increasing SR. And the absolute value of the P decreases with increasing the inverse length from 2 to 20. Why? Because K is inversely proportional to the radial thickness. So it increasing in the K decreases the radial thickness, that decreases the pressure drop. Here we can see the induced electric field strength EX variation along the length of microfluidic device for various surface charge ratio and at ST equal to 8 and K equal to 2 and 20. Induced electric field is maximum in the contraction section as compared to the upstream or downstream sections, because the reduction in the cross-section area increases the excess charge and convective velocity in that section, that increases the steaming current or induced electric field strength in that section. Induced electric field decreases with increasing inverse length from 2 to 20. Why? Because the K is inversely proportional to the radial thickness. So the increasing in the K decreases the radial thickness, that decreases the excess charge. So the induced electric field decreases with increasing K. So the maximum value of induced electric field increases with increasing SR, surface charge ratio SR from 0 to 1, and decreases from with SR SR increases further 1 to 2. Why? Because increasing in the SR enhances the electrostatic force near the wall, that increases the maximum value of induced electric field, but at higher SR and small k, when EDL overlapped, the forces are much stronger and resist the charge flow that reduces the streaming current or induced electric field. Now, pressure P variation along the length of the microfluidic device for various surface area ratio and at ST equal to 8 and K equal to 2 and 20. So the absolute value of the P decreases with increasing in inverse length 2 to 20 or ideal thinning. Okay. So the absolute value of the P decreases with So the absolute value of the P increases with increasing surface area ratio from 0 to 2. Why? Because increasing in the SR enhances the electrostatic force near the wall that increases the wall stress and resists the flow. So the pressure drop increases with increasing SR. Okay. So now electroviscous effect measure in terms of electroviscous correction factor, and electroviscous correction factor is defined as the ratio of vector viscosity to the physical viscosity or the pressure drop with electroviscous effect and without electroviscous effect. Where the vector viscosity is the viscosity of the liquid to obtain the pressure drop without electrical force. That relation holds good for a steady Rhod's number flow when the non-linear advection term in the momentum equation is negligibly small. Here we can see the electroviscous correction factor variation with SR at ST equal to 8 and K equal to 2 and 20. Electroviscous correction factor shows proportional dependency with SR and inversely proportional dependency with K. Because pressure drop increases with increasing SR and decreases with increasing K, as we discussed earlier in earlier slide. Okay. So when electroviscous factor is 1, there is no electroviscous effects, and the electroviscous effect comes into picture when electroviscous correction factor is greater than 1. Okay, so now comes on the conclusion part. Poisson equation with NS, NP, Navier-Stokes in conjunction with Planck model equations have solved using the finite element method for given range of parameters. Contraction expansion in the geometry increases the excess charge, potential drop, and pressure drop due to reduce in the cross-section area. And the asymmetry of the surface charge affects the total electric potential, charge, pressure drop, and induced electric field strength. And further, the electrostatic correction factor increases 17% with increases surface area ratio. So overall, the electrostatic effect increases with increasing the surface charge ratio of surface charge asymmetry. These are the references. Thank you.